Hello everyone. Today we analyze the model vibration analysis using force excitation or experimental model analysis using shaker, dynamic shaker. This type of analysis is conducted when the structure is big enough, which is not possible to excite by the uh, like impact hammer. So for that purpose we used to or excited by dynamic shaker. Now let's see how exactly the setup has to be made. For this analysis, we require the following instrument. One is this shaker, stringer, force transducer. Now here the shaker is connected to the amplifier. The function of the amplifier is to amplify the signal up which is coming from the function generator. Here function generator is used to generate the desired frequency at which this dynamic shaker is vibrates, and the excitation force is measured by the force transducer. Responses is measured by the accelerometer at different point along the length of the beam, and these two channels to this force transducer and accelerometer are connected to the FFT analyzer. Here is it is connected to one and it is connected to two. If more channels are there, you can connect more number of accelerometer to get the simultaneous data. Now here this FFT analyzer is connected to the computer to control and for interfacing all this one. So this is the basic setup we required and we will use here for analysis purpose. This is my experimental setup. Here is my computer. Computer is connected to this one is FFT analyzer. This is my FFT analyzer, 2-channel Oro analyzer.
Two channel. This is channel number 1. This is channel number 2. Channel number 1 is connected force transducer. This is my force transducer. This will measure the excitation and the responses will be measured by the accelerometer which is attached to the structure. Here I have taken a structure of this external system 1 feet this ruler. Now for exciting the structure, I have the dynamic shaker. This is my dynamic shaker. It is connected to the amplifier. Amplifier is connected to a function generator. Function generator is used to generate the different form of waves, sine wave, square waves, random waves, pulse, noise. So we will use for exciting this structure sine wave of 1 Hz. Now let us see how it works. Now I have started it. Now you see it 1 Hz it is working. Now it is exciting my structure. This exciting force will be measured by the force transducer and this will measure the response.
Now we will set up the analyzer's parameter, signal parameter, and we are using here Oro's 2-channel analyzer for this purpose. Now I have opened this Devash's project. Already I have made it. So I'll just check the signal parameters, and if anything is required, we'll change it. So this is my interfacing software, basic expertly this exclusively used for the Oro's analyzer. Now here is you can see this is my FRA, this is my coherence. This is my coherence and this is my input channel, means the force, and this one is this input of 2-channel, means the response it will measure. Excitation will be shown here. This is FRF, and how the response is acquired by the accelerometer will be measured by the coherence. Now I am here checking the parameters. So my channel 1 is connected to the force transducer. You can see here, this is my sensitivity 2.9. Automatically it is selected by the software. Here maximum range is 10 millivolt. Okay. AC supply, simulate channel number 2. Accelerometer, unit is meter per second square. This is my sensitivity. Again it is measured automatically by the instrument. Now here there are two channels I have. Now I am using so I don't have to do here. Here also I don't need. Now here I can change the type of what unit I want to take. The basic unit, like here for Newton, I am taking one unit. Similarly for frequency range, I am taking 0 to 1 kilohertz. Now I'll take for the, here I have changed the linear unit. Now I'll change see the channel number 2 accelerometer. Here 0.1 meter per second square return, so I'll just convert into 1. Frequency range 0 to 1 kilohertz I'm taking. Now here I am increasing the averages. How much averages for the data I need? So I'm taking 5 data. 5 averages I'm taking. I can increase if I wish. Now overlapping, you know that overlapping enhances the real-time data frequency, which is visible on the computer, and that's why I'm taking here 75% overlap. Now here you can see resolution is 1601 because resolution of this analyzer is less, so I'm taking this much data. Now this one is a complete signal processing I have done. Now I want what data I want to save in the laptop. So for that I don't require cross phase spectrum, I'll just require FRF of a structure and I'll save it. I'll again try here. Now UFF file format, universal file format I am taking. Now I have saved this data. I'm exporting this data, means where my data will be saved. So this is the folder where this data will be saved. I can change also. I'm trying to save it on a desktop in a particular file. I have done this. Now I'm taking the excitation here. You can see here. Now you can see the, this is my FRF. This one is a coherence. Coherence you can see here 49% is showing. This one is a responses of the excitation given by the, here you can see the excitation is slightly less, that's why here this uh, coherence is also seems to be less. This is not a good means value should be 80 to 90% in order to get a good data. Now you can see here, I'll adjust again this retake the data. Now here at the bottom you can see 5 averages I supposed to take. This is the minimum frequency, millihertz I can, resolution I can take. The total time duration of data will be 3.2 seconds. Now I'm saving my data. I'm just trying to save this acquired data. I can retake as much as number of times I want if data are not good, but just first data I want to ensure that the FRF goes to the right folder. Now you can hear the voice also. So this is the impact. Here you can see the coherence value. This is my citation. I can change the scale also here. I can change the scale also, so I'll do that. This is my FRA. Now you can see the responses of the accelerometer. This is here. It is impact of the this force transducer. Now I'm saving one by one. Data are being saved here. Now here resonance, this coherence value is very less, so I'll not save this data. I'll take again the data. You can see 90%. So here I can take, I can save this FRF. So 90% or above data are considered good enough. I'm saving my data here. You can see 80%, 88%. This is good. I'm again running it. Now you can see this is how I'm acquiring the vibration data. This is my beam, accelerometer, force transducer, stringer. I'm exciting the structure with 1 hertz frequency. Now I'm changing the location of the accelerometer. Now I'll again acquire the data. So this is how we used to acquire the vibration data here. Now if I have a now we are going to less these data are not good, so I used to take the repeat data. Means when the responses are not good, it's better to, here you can see the you 5 after 5 automatically my this FRF will be stopped, though this will show the impact continuously, but it will not be recorded in the analyzer. This data are supposed to be saved, so that's why they will stop, even though the real time they will show the impact, but it will not be recorded here. So 87% I'm taking, I'm saving this data, and again I'm exciting this structure. Now here, now you can see that it is, these averages are changing. For very, less than a second, this one average is complete. So again this one is 37, so I'm not going to save this. I'm going to again reacquire this vibration data. Here you can see 82%, so I'm taking it anyway. This is how I'm doing this. Now once the vibration data are collected in a file, so these are the vibration data I have collected. Total number of data are 12. I saved in a file. So this data have been saved here in a file. Now I'll close it. I'm saving the configuration and I'm saving this. Now these are my FRF. Data acquisition process is now completed. Okay. Now I have opened the Emiscope software. Wait. Now let's try to understand. This is my Emiscope software here. Now if you see here, this is the point I have created. I have just marked it red, and then I have created number of points here on the this window, and I have given them direction, means x, y, z. You can see here x, y, and z. So I'm giving the beam length along the x-axis. So 1 to 12 data I have selected here. Then next 1 to 12 data I have selected in the x-axis, but the distance I have taken along the z-axis. That's why it is looking, you can see here along the z-axis. So this one is 1 and this is the 12 length. So here you can see 1 to 12, then 1 to 12. Again here at the distance of 1. So here is my 1 distance I have taken. Now I am arranging this data in a format. You can see this. I have converted into single window. Now I have, you can see a number of data I have taken here. This red indicates that if I click here on the mouse like this, so I'll just find a new data here. Now I'm changing the coordinate axis. So this is x-axis, this one is z-axis. Now y-axis, I'm exciting the structure. So at present I'm taking 0y. You can see in all I'm taking 0. You can see here. So this is how we'll create the structure. More complicated structure means it will take more time. If the simple like a beam, cantilever beam, it's a simple structure. So maybe within 5 to 10 minutes I can create the structure. You can see since I have kept my structure, this accelerometer at the midpoint, and that's why I need to create at the 0.5 distance from the Y. And that's why again I'm creating at the mid of 0.5. If I this is 1 inch, so at 0.5 inch I'm taking this data at midpoint along the length of the x-axis. So this is how I have created all these points. Now there are some data are missing, so I'm just trying to find out them in a to make them correct. See, another data I have missed data have been found, and now I corrected it. Now my data points are completed. Now two still some 2 3 data are I'm finding they are random, so I'm locating them in their appropriate places. Now I am since my data are completed, so now I have keep this red point with line, so I'm connecting all the dots together. You cannot have your independent dots. All dots should be connected with line, then only your structure will sense the vibration. Otherwise your independent dot will vibrate if you connect one FRF to it, and it will not affect the complete structure. That's why we have to connect all the data together with in a with a line. So I'm connecting it one by one. It's your choice uh, which data you want to connect first. It's up to you, and it doesn't have any effect on the geometry. So I'm doing randomly here. It's taking a, it's a very minute work, takes time. To make a geometry perfect, you have to be very uh, patient, and then you have to you know join the desired data only. If you join the randomly, then the geometry will be damaged. Now here you can see some data are missing, and that's why my geometry, this is my reference. So I need to have some more data. I have already some data which was missed, so now I want to place them in an appropriate location. Now you can see one data I have already put here. Now another data already again I have put it here. Now I'll again join them with the main geometry with a line. Now my geometry is completed. You can see. Now I'll create area. First data, then line, then area. So for creating area, any three dots are need to be connected. So that will give you the area in form of triangle. So this is how, as much as area you want, you can do it. It will not have any effect on geometry. So I'm doing it here randomly, but ensuring that my complete geometry is covered with the red color area. If you miss it, then the area will look blank. Now here also you have to perform it very patiently and do one by one. You can see one by one I'm doing it. Now this is my geometry is completed. Now I don't require here this one. So this is my complete geometry. You can see here. Now there is an option in the software itself. Suppose you want to create the already created geometry. So for that you can have this option. There are number of machines and other things are already inbuilt feature. So you can take directly those geometry for your creating your customized geometry. But if you don't require, you can create your own like we have done. Now I need to label them where my accelerometer will be fixed. So that I'll do. First, extra point, if any, they can be hide by using this hide option. So I'm clicking these two extra points are there, so I'm just hide them. Now I'm giving the label. You can see point label I'm giving here. So you can see, yes, I have point given these points. So my points are visible on the geometry itself. Now I have fixed, means the portion which supposed to be fixed I have given with name is F. Now rest of the points are labeled as 1, 2, 3 in a sequentially in the same order as I have taken the FRF. You can see here. So instead of fixed, I'll write F. I'll write fixed here, so it will be better visible. These are visible now. You can see here. This is my geometry. Geometry require time, almost as much as the data acquisition time. Now you can change the direction, orientation of the geometry as well by using the view control, 3D view you can see. So at appropriate location you can fix, and then you can analyze all the direction you can see, so that you can ensure that your data points are uh, you know fixed at particular orientation and no at different location than desired. Now you can save my geometry. I'll save it with the name cantilever for force vibration or any force excitation. I'm giving saving it in a binary structure format. So this is how I have saved. Now by clicking this option, I will give the boundary condition. This portion, the portion which I have written F or fixed, need to be fixed physically in the software by selecting these points. Now you can see I'm going to those points. So I'm selecting those points. So these points are now highlighted. You can see here, these points are highlighted. Similarly, all these points are highlighted. Now there are different options here. Vector, restraint. So I'll select vector, and then both magnitude and displacement will be fixed, and I'll save it. And then again I'll click here. So this will go. Here you can see this. Now I'll import my FRF data. Now here data is structure data I have taken, whatever data I have acquired. So all these are imported in the software. You can see now I'll select here degree of freedom. I'm giving roving degree of freedom because my accelerometer is direction was changed. So after y direction I have given means the structure may rotate in any direction. So this is my fixed here the frequency you can see. So I have changed it. This is one FRF are shown. I will take here the cursor I have set complete. Now here all the frequency I want to take, so I just set the cursor on the extreme limit. Now I'll take model parameter. I want to acquire the model parameters. Now I'm taking all data together. Overview format, you can see here overview format. I'm taking model parameter. So now how much count I have, I will just, you can see these are all probable mode shapes. So the software has counted. Now this is the natural frequency and corresponding this damping ratios I have observed. Around 14 mode shapes I have observed. So I'm taking quadcopter and saving this mode shape table. So these are the two parameters you need to write. This is your damping value, this is your natural frequencies. Okay. Now here if you observe this one, this natural frequency, as you know, the structure can have an infinite number of natural frequency and corresponding mode shapes. And obviously you'll get some values of damping also, but excitation at what means, if the tip is hard, then you will get higher frequencies only excited. If tip is soft, then lower frequencies will be excited. Some mode shape may not visible in the uh, uh, this FRF, and that's why the same mode shape will not be visible. So if some mode or natural frequency may skip also, it depends on the excitation process. Now I'm assigning all this FRF, and what I have done, if you look at here, what I have done here, I'm assigning M means FRF here. Now here you can see there are two options. Graphical assignment means 1, 2, 3 you can select, so it will be selected, or you can do mesh point number and degree of freedom. So automatically it will be done by the software. You need not to do anything. So automatically they are now selected. Now I'll try to animate the mode shapes. Now here how much point need to be get influenced by the one excitation, so you can increase or decrease that one also. You can see here those things. Just wait, I'll just show you here. Here, so these are 6 points I have taken. You can take 4, you can take 2, or you can take 10 also. The more number of data point if you have taken, means more data will be influenced by a single excitation. Now I have animated the structure. I can select the, these are the mode shape number. Variations are I think not too much visible here. So it's a hit and trial method. You can change the this degree of freedom also. Some points are excited too much. It may be, it depends on the FRF. If you are taking some FRF are acquired with high coherence, will vibrate with more deformation. So in that case you can enhance the number of data points to be influenced in this here by selecting this point. So you can see this is how my structure is. Now some variation are there. If I am selecting this one, so some variations is there, but you can see here. Now here is my frequency at what this structure vibrate, and this is the deformation. So when I change these points, so these points are also varies. For example, if you can see here, frequencies are changing here. Now I'm again uh, just synthesizing the FRF. All this FRF I am taking here in a new data book. Here it's since one of the mode shape was selected only, and that's why you can see here this was selected, and that's why only one peak was observed. Now I'll again do this. Now you can see all the peaks are you can observe in the table. Now you can trace them in a different way. There is an option here, format. For example, spectrogram. This is spectrogram. All peaks are visible with this color code. Similarly, all the these peaks corresponding to their FRF, you can see in a three-dimensional graph. You can observe. This is my this body plot. Here this is border plot. Here if border plot is nothing but a graphic graph which consists of phase phase versus frequency. FRF consists of two diagrams. One is amplitude versus frequency, and second phase versus frequency. Means amplitude, how much deformation is taking place in the structure corresponding to the frequency, and second graph indicates how much angle actually the structure vibrated from the reference. This is my reference. So how much, whether it has vibrated in a positive direction or negative direction, it shows by this graph. We call it body plot. Here you can see individual, this is individual graph. Now you can see how the structure is vibrated. You can it is shown. So here 0 to 180 degree, and again here 0 to 180 degree. So this is a single FRF. All the 14 peaks you can observe here. All 14 peaks are observed, and how the structure is vibrated along the frequency. So these are given here. Okay. So there are different format. You can see it. So this is how also you can get your. So all the FRF are, when you merge them together, it looks like this. So every FRF there you can have the magnitude and the phase. So phase, obviously for individual FRF acquisition you will have a different phase, because we are taking the we are acquiring vibration data at different points. So when change the location, obviously phase will also change. Now this is here the another diagram, that is displacement versus, here you can see displacement versus frequency. As I told, there are two graph in FRF, amplitude versus frequency and phase versus frequency. So this is my amplitude versus frequency, and all these things you can see here. Again, through using this, when you change the cursor, the vibration characteristic of the beam will also change. So I have just you know now you can see here, if you change the mode number, slightly some variation is there. This is how you can vibrate your structure. See this variation is small, but when you visible this carefully, if you observe, you'll see the differences. Now through this you can increase the amplitude also. Now when I synthesize this FRF, see here. This is how you can get it. You can save this figure and you can use in your analysis in a report. So there are different types of graph you can get it. You can get the real and image, this real part also. There are different form of graph. Your data vibration characteristic can be, here is a spectrum. You can represent it, you can save it. Here you can see it's a 3D diagram of vibration characteristic. You can change the direction, magnitude and other thing also. So this is how you can do it. Now suppose you want to make a movie of your mode shape, then it is also possible. You can use it for your analysis also. So suppose you want to take the movie, then there is a option here. You can select this one. Here you can, if you want to increase the amplitude, you can select this point. Then you can make a movie of a complete window and you can represent it wherever you want in a presentation. So that is how this is a movie diagram you can see. Now you can save it in a particular folder wherever you want. So this is how you can do it. This is a movie window, it is open. So this is how you can conduct your model analysis in a different steps. Say just for demonstration, in a real structure like chassis of a car, airplane wings, and like a helicopter blade, uh, there are so many application it has. So sometime we require this setup and the procedure we need to understand so that we can use it. This is Emiscope software is a old one, almost 12 to 15 years, but nowadays much more sophisticated instrument as well as software has arrived, and maybe you won't face too much difficulty what we have seen here. But yes, it required procedures are same here even today also, same procedure you need to follow. So with this, thank you very much for watching this.